Hey guys, welcome to this video on imaginary numbers. It's a concept that you may or may not have heard of before, so let's take it right back to the start and go through that way. So what we're going to do in this video, well, we're going to define what imaginary numbers are, we're going to look at some of them, we'll talk a little bit about the history of imaginary numbers as well, and where you might have actually come across imaginary numbers before. We're also going to talk about or extend on it and talk about imaginary numbers as complex numbers. And there'll be a few more terms and symbols that you may not have come across before, which we'll explain when we get there. So let's start off by looking at what can we define an imaginary number as? Well, it's any number in the form of a plus bi, where a and b are real numbers, and I is the square root of minus 1. And we call this a complex number. So you may have tried before to put the square root of a negative number in your calculator. It's going to come up and say, error, can't do it. It's just not going to work. And in fact, if we give it a shot on my calculator, if I get it out, if I go, let's go minus 3 minus and square root that, it comes up with an error. So that's because it's not set up to do complex numbers. Some calculators will actually let you do complex numbers. What might be a setting on the ones we use, I'm not 100% sure on that, but we might investigate that a bit later. You might remember back to when we were talking about quadratics and polynomials, that when we're using the quadratic equation, that's the minus b plus or minus the square root of b squared minus 4ac divided by 2a, that if we found the discriminant, which was a triangle here, which is just that b squared minus 4ac, which appears underneath the square root sign, or the radical sign as we now have come to know it, that if our discriminant was greater than 0, then we've got two real distinct solutions. Or we can find two numbers, or there's 2 points when we graph it, that it crosses the x-axis. If we found that it was equal to 0, then it touched the x-axis once, and that's it. So it was two real identical solutions, or just really one solution to it. However, if the discriminant was less than 0, we found that there was no real solutions. So we've sort of come across the concept of these imaginary numbers before. We just haven't really given a name to them or really looked at them. Now, where did all this come from? Well, in 1572, a mathematician by the name of Raphael Bombelli defined the imaginary number as I being equal to the square root of minus 1, and we call it imaginary because we can't actually place it on any number line or any real number line. We can only place it on an imaginary number line. And in fact, if you're planning to do specialist maths next year, we actually look at different number lines and can look at having a real axis and an imaginary axis for sets of coordinates. So with I being defined as the imaginary number, we can write down solutions for quadratic equations where the discriminant is less than 0, and we call these complex solutions because they include a real and imaginary parts to them. So complex because we've got both of those parts. Let's look at some of the maths behind it and what you guys are going to be doing. So if I have x squared being equal to minus 4, I want to solve for x. I want to know what x is. Well, the first thing I would do in any case like this is take the square root of both sides because we want to get x by itself. However, that would mean that x is equal to the square root of minus 4. And we've been told you can't have the square root of a minus number, except turns out you can. We just call it imaginary. So in this case, x is going to be equal to 2i, and it's plus or minus 2i. It can be either one. So, because really this is just going to be the square root of 4 times the square root of minus 1. We can split square roots up like that, or radicals up like that. And we get the answer being plus or minus 2i. And that's really what it boils down to. Whenever we've got something squared like that, we can do things like that. What if I've got, let's look at another quick example. X squared plus 9 being equal to 0. Let's try and solve this. Well, in this case, we're going to make x squared take 9i squared being equal to 0, because we're going to use that to be able to split it up. And if you look at this, you can probably see that it's now the difference of two squares. So that means it's going to be x plus 3i, x take 3i being equal to 0. Therefore, x can equal plus or minus 3i. Again, an imaginary case. We'll look at some more examples of this in class. So what I want you guys to do now is just get this written down, look at these examples, get these examples written down and understand what's going on here. And then I'm going to go on with complex numbers. So pause the video, get this stuff written down, and we'll see you in a moment. Alright, so hopefully you guys have got that written down. Let's move on to complex numbers. So let's just say that I've got z here being equal to a plus bi. That is, the a is the real part of z and b is the imaginary part of z. The way that we write this out is a being equal to this re, and it's a sort of funny cursive script that gets used of z, and so re, z, and b being the imaginary part. So this is real, this is imaginary. And just think about it as re and im. So how do we perform mathematical operations with complex numbers? Well, it's exactly the same as what we would normally do. If I've got something like 2 and I go 3 plus 6i, that's still just going to be 6 plus 12i. It doesn't matter, it's still going to be exactly the same. We just treat it as the I being on the end of it. It's an imaginary part. That doesn't mean that it's a figment of people's imagination. It's actually a proper number, just not real in the sense of it fitting on a number line somewhere. So, and we can do things like the multiplying by the conjugates again if we wanted to get rid of the imaginary part off the bottom, which we'll go through an example of that in a moment. To addition, subtraction, multiplication, everything, it still works out exactly the same. So let's look at a few examples. If I've got z being equal to 3 plus 2i and w being equal to 4 minus I want to find z plus w. Well, that's just going to be 3 plus 2i plus 2, sorry, not 2, 4 take I, which we can see we'll just add the real parts together and the imaginary parts together. So 3 plus 4 will give us 7, plus, so we've got 2i take I will just be I. So perform by same operations as what we've been doing. If I was to go minus, it would still work out the same. If I've got zw, so z times w, let's do that one. So that's going to be equal to 3 plus 2i and multiply by 4 minus I. And what this is going to be, let's work it out. We've got 3 times 4, which is 12, plus 8i take 3i take 2i squared. So you've got to remember that in this case, there's going to be that I squared part that'll come into it. So what will this be in the end? Well, let's look through. We're going to be 12 plus 5i take 2i squared. However, I squared and I squared, or if we would make it what? Have a think about it for a moment, and then I'll tell you the answer. Well, think of it this way. If I is just equal to I being equal to the square root of minus 1, if I square that, suddenly that will become minus 1, wouldn't it? So anytime that we've got an I squared, we can just change it to a minus 1. So that would mean that we're going to have 12 plus 5i plus 2. And the reason it's plus 2 because minus 2 times minus 1 will give us plus 2. So that means that our final answer would be 14 plus 5i. Hopefully you got the same thing that I did. We'll do one more example of this, and then we will move on to the next little bit of it. Our final example is going to be, and I'm just going to draw off a section here for us to work in. Our final one is going to be z divided by w, and this is where we're going to use some of the stuff that we learnt about before when we're talking about radicals in multiplying by the conjugate. So what this will be is 3 plus 2i divided by 4 minus I. What we're going to do, we're going to multiply this by the conjugate, which is 4 plus I. Again, the rules are the same. All we do is just change the sign. And what this will do, we'll get rid of the I down the bottom eventually. So if we expand this out, we're going to have 12 plus 3i plus 8i plus 2i squared divided by 16 minus I squared. Now, let's collect our terms together. Let's fix the I squareds that we've got there. And what this will become is 10 plus 11i divided by 17. If you're not sure, have a look through, just think of the process, and we could write this in the form of a plus bi as being 10 over 17 plus 11 over 17i. So an important point to take away from this, so get all of this written down, but another important thing to take away, if we've got I squared, that's just going to equal minus 1. Get this stuff written down, and then I just want to talk about the equality of complex numbers, and we're going to be finished with this video. So pause the video, get this written down. Alright, so the last little bit here is the equality of complex numbers. So two complex numbers are equal when their real parts are equal and their imaginary parts are equal. So if I've got a plus bi being equal to c plus di, that means that a must equal c and b must equal d. If we wanted to look at a proof behind this, it's in the textbook, and we might go through that in class, but in terms of this video, I'm not going to include it. Let's look at a quick example. And this is find real numbers x and y such that x plus yi multiplied by 2 minus I is equal to minus I. Whew, that's a bit of a mouthful to say. So let's see how much of this we can work out. So we're going to have x plus yi by itself. Let's keep that by itself because we want to find what x and y are equal to. That means it's going to be minus I divided by 2 minus I. And what we can do is multiply this by its conjugate. So minus I divided by 2 minus I multiplied by 2 plus I over 2 plus I, which means what we're going to have up the top is minus 2I minus I squared divided by 4 minus 2I plus 2I, which just leaves us with 0. Take I squared, which we know is just going to be 1, so plus 1 in this case. So that means that we're going to end up with up the top here of minus 2I plus 1 divided by 5. And we can work out from here what x and y are going to be. So let's rearrange it so we've got the real part first, followed by the imaginary part. So we're going to have 1 divided by 5 plus, oh no, sorry, in this case, minus 2 on 5I. So that means in this case that x is equal to 1 on 5 and y is equal to minus 2 on 5. And that's the equality of complex numbers. So that's all I really wanted to talk about in this video. I do apologise that it's a little bit of a longer one and there are lots of complex concepts to go through, but if you do have any questions, as always, just ask. Thanks for watching and we'll see you next time.